Good morning. Welcome to Krishna's classroom. Last time we introduced the Baire's category theorem and discussed the proof of the theorem. Now what we want to do is to look at some applications of this fascinating theorem. In fact, we begin with a very interesting application of this theorem stated below. Now, we have the following theorem, and while proving this, we make use of Baire's category theorem more than once. Let X be a complete metric space let Fn R be a sequence of continuous functions assume that there exists a function x to r such that Fn x converges to f of x for each x belonging to x as n tends to infinity. That means we are assuming pointwise convergence of the sequence. Then what we would possibly look for, question that we ask is f going to be continuous? It is the limiting function. Can you assert that limiting function is continuous? Then what we can assert is that the function is continuous on a dense subspace of x, not necessarily on the whole. There exists a dense subset D of x such that each point of D is a point of it is possible to construct examples where the limiting function may not be continuous everywhere. But what you can say is that there is some dense subset of x on which the limiting function is continuous, or you are just making a statement that it is nearly continuous everywhere, okay, or continuous nearly everywhere. That's what we mean by that. So on a dense subset D of x, the limiting function is continuous. Now we shall look at the examples possibly later, but let us prove this theorem. So I believe it is clear. We have a sequence of functions from x to r, and each fn is assumed to be continuous. Then assume that there exists a function f such that fn converges to f, such that fnx converges to fx for each x belonging to x. That means fn converges pointwise to f. Then what we assert is that there exists a dense subset of x on which and at each point of which the limiting function is continuous. So let us prove this theorem. The first job is to identify the space on which, or the dense subset D, on which the function, on which possibly the function is f is continuous. And this, it is in this scenario that the Bayes theorem comes into use. So let us start proving this theorem. So first task is determining a possible dense subset D on which that's our first task. So we proceed as follows. Fix epsilon positive. Now define k belonging to a the class of natural numbers such that where a set ek defined by is less than or equal to epsilon. That's how the K comes into it. Well, this is well defined. The reason is that Fn converges to F. Therefore, Fnx is a Cauchy sequence. So, for each x belonging to x, Fnx is a Cauchy sequence. Therefore, this set Ek is well defined. Note that Cauchy being convergent. Now, what we claim is this. Is closed form. So that is what we want to establish first. So let us prove this. How do you prove this? Make some remarks on this theorem later. So fix epsilon positive. Okay. So fix Mn greater than or equal. Then define Enk K N M epsilon to be. So we are fixing M and N for which mod Fnx epsilon. So for each M and N greater than K, we define the set E K N M X. Okay, we are fixing those numbers. Define it. Now the first observation that we make, E K N M is a closed set. Now this is because Fn minus Fn is a continuous function. And we are actually taking the what you call the pre-image of 0 to epsilon. Okay, and we are taking the pre-image of this. That means the set of all legs which gets mapped by mod Fn minus Fm into this class. It's a closed set. This is continuous. Therefore, see that the set Eknm epsilon is closed. Now let me just write it this way. I am using a symbol. That means the set of all points gets mapped into the this is closed. It's the inverse image by a continuous function of a closed set. Therefore, it is. So this is the explanation. That okay. Now observe that Ek epsilon is equal to writing and Mn so this is the observation. That's quite easy to see. Okay, one can easily prove this, and each one of these is closed, and this is the countable intersection of closed sets. Therefore closed sets so we have proved this, that Ek epsilon is closed. Now what we observe is the following. How X is related to these Ek's. Next we claim X is equal to N over K Ek epsilon. This is quite easy to see. For let all that we need show is that x naught belongs to one of the Ek's. Okay, since x naught n tends to infinity, fn x naught push. Hence, given epsilon positive, there exists k naught such that for k naught mod and that implies x naught belongs to, it is a simple, very direct thing. Ek naught. So it belongs to one of these Ek's, and therefore every element of x is in one of the Ek's, therefore x is the union of x. That completes the proof of that. Now we apply Baire's theorem. Okay. At this stage, the stage is set for application of the Baire's theorem. Now x is complete. And x is equal to, which are all close to subsets of x. Okay. Therefore, by Baire's theorem, by Baire's theorem, we have the following conclusion, namely that the u epsilon is equal to what we conclude is this. Hence, by Baire's theorem, one of the Ek epsilon has an non-empty interior. Has a non-empty interior. So that's a conclusion from the Bayes theorem. And therefore, let us now define U epsilon to be union of K interior of because one of them is non-empty, therefore you see that U epsilon is non-empty. Okay. Therefore, you see that the interior is anyway open, therefore U epsilon is open. Then U epsilon is a non-empty open subset of X. Now what we do is we just change the notation slightly for convenience. Slightly change the notation. So note the slight change in notation. Let us redefine. U1 by. So U1 by n we write as UN. I mean that's for convenience. Every time, otherwise you have to, because you see you have defined U epsilon. Now what you are taking is, you are taking epsilon to be equal to 1 by n. So it is U1 by n that you are talking about. But for convenience, in our later write-up, we just use UN. Okay. Now what we claim is this. That is our next claim. So this is our next assertion. What we assert is this claim strictly speaking, our standard notation, it is going to be U1 by n. Is dense in X. So let us prove this. So we shall prove this. So we have come to the new class of sets, namely when in between we have made an application of the Bayes category theorem. Get hold of that. So to show this, to prove this, we choose an arbitrary x Now, we show that every closed ball see, we are proving the density. Every closed ball B given by EXR, which in turn is the set of all y belonging to x, such that D of is a closed ball of radius r centered at x. It's a closed ball. I mean, that's something to know. So we put a usual bracket if we are talking about the open ball. Now we are talking about the closed ball. Has a non-empty intersection here. If we show this, then you see that you take the closed ball centered around x, any closed ball, because R is all positive radius, then it has a non-empty intersection with particular un. Therefore, you see that un is dense in X. That's the argument. So let us prove this. Now B is a, this is the definition. This is the definition. B is a closed and therefore completeness so B is complete. Now B is then equal to union N of B intersection EK that is coming from there. See, we have earlier shown that x is equal to union k ek epsilon. Therefore, you can over it has to be k That is, it's a countable family of closed sets. Okay. Therefore, by Bayes' theorem, it's a second application of Bayes' theorem. By Bayes' theorem, at least one of them has a non-empty interior. At least one of them has a non-empty. At least one of them interior. Interior of this not for some k. Okay, for some. Now we observe that interior of contained in that's straightforward. It follows that B is not empty. You are given, of course. This we have defined earlier. So what have we proved? We have proved that every x has an element uh, in every closed ball B XR has a non-empty intersection with L. That's what we have. That's what we have. So this is the outcome. So what next? Next so this enables us to define the set possibly on which that is a dense subset of X on which F is going to be continuous. So now we define D as UN. UN is actually U1 by F. Okay. So what can you say about this? See, each UN is open. Okay, right? And therefore, the countable intersection of open sets is open. Therefore, D is open. By definition, U is now a countable intersection of open sets. Further, X is complete. Therefore, D is dense in X. So that is now what we do is, so we have identified a dense subset of X given by D. Now what we claim is that claim every for every x. That's what we want. Okay. So we have already done the spade work of identifying the dense subset, and now if we prove that f is continuous on D, our work is complete. So we go over to the last level. Okay. So for that, fix let epsilon possible given. Now choose such that this is possible. These are all very routine things. P belongs to D implies yeah. And hence there exists K positive such that P belongs to the interior of so we start with a point P, an arbitrary point P belonging to D, and then conclude that P is in the interior of EK 1 by for some K. By continuity of Fk, Fk is continuous everywhere. Therefore, it is in particular continuous at P. There exists an open neighborhood V of P contained in interior of such that is less than epsilon for every x belonging to. Now, for x belonging to V is contained in E K one by n by the definition of E K epsilon we have E K epsilons, we have one by n equal to k. Now letting m tend to infinity, fmx goes to fx. We have less than or equal to for every x belonging to V. Now we claim that three epsilon. Now that would completely prove that f is continuous at the point. So we estimate. It's very easy easy estimation. Less than or equal to plus fk. Okay, so we estimate this. Now this is less than or equal to 1 by n plus epsilon plus 1 by which is less than. Now that implies f is continuous. Now this is the usual technique of proving this. Okay. To go from, to estimate this, what you do is to get the inequality fkx minus fk, fx minus fkx, and then you have an estimate of that. Then you have an estimate of fkx and fkp, because going from the point x to p, that's in V we are working with. Therefore, you have an estimate of that. And then at the point p, again the same sort of estimate like fp minus fkp. Okay. So the first two estimates are of the same class. The middle one is on fk. So you have something like fkx to, this is fkx, this is fx. So you use this fk converging to f at x. So you use this sequence fk x. Similarly, you also use this convergence of fkp to f. These two we make use of in these two stages. And at this stage, what you do is you keep fk, so you reach out to fk, and fk you evaluate at x and fk you evaluated at p, and then say they come closer to each other because of the continuity of fk at the point. So we make use of the continuity of fk at p, and then we do this. Therefore, f is continuous. Now that's the proof. So that completes the proof of the theorem. So f is continuous at every point of t. That completes the proof. We conclude the talk today at this stage, and then possibly come with some examples next time and look at other applications of the Baire category. Thank you very much.